A diversity of grasses stretch across lush fields and prairies throughout the world. Truly, they are a beautiful embodiment of the harmony of nature. Or so you might think. Are fields of grass filled with fugitives? To answer this question, we need to understand the game of grass. Our grass quest takes us to the prairies of the Cedar Creek Ecosystem Reserve in Minnesota, which contains on the order of 40 coexisting species of grass. For these grasses, nitrogen seems to be a key limiting nutrient. From the competitive exclusion principle, you would expect the species that's the strongest nitrogen competitor to competitively exclude all of the others. Long-term competition experiments support this idea. Little bluestem, which I suppose is our grass champion, tends to drive nitrogen to the lowest level in common garden experiments and competitively exclude the other grasses. On the small spatial scale of gardens, these grasses don't seem to coexist. So what's going on the larger prairie scale? Well, maybe what we have is a prairie full of fugitives. Over the years, scientists measured how quickly grasses colonize fields and how efficiently they utilize nitrogen. Long-term research suggests an interesting trend among the 5 most common species of grass. On this plot, the x-axis shows the resource use efficiency of each grass species. Specifically, it shows what's called the R-star of each species, how low each grass species tends to drive nitrogen levels. The lower the R-star, the better it is at competing for nitrogen. The y-axis shows observations of how long it takes each species of grass to establish on an abandoned field at Cedar Creek. The larger the value, the longer the establishment time, and the poorer the colonizer it is. Species that take longer to colonize a field tend to have a lower R-star, and species that take less time to colonize a field tend to have a higher R-star. The weak competitors colonize fields rapidly, and the strong competitors colonize fields slowly. This suggests that something like a competition-colonization trade-off is happening. So why might things look like this? Well, some work suggests that different grasses invest in different strategies. This is a bit like everyday life. You have limited resources. In your finances, you can't invest more money than you have. You have a limited budget. At least most people do. So you have to decide what you invest in from your finite resources. And the same is true for grasses. They acquire a finite amount of energy through photosynthesis and then invest that in different life history strategies. Some grasses invest the majority of their energy into growing deeper roots, while others invest their energy into reproduction and growing more seeds. Allocation of resources into roots allows the species to extract nitrogen more efficiently from the soil, which makes it a better competitor. For the 5 grasses at Cedar Creek, species with lower R-stars, meaning grasses that are stronger nitrogen competitors, have more massive roots. Reproductive investment means producing more seeds, which allows grasses to disperse more propagules throughout the environment and colonize it more rapidly. Because resources are limited, grasses simply can't do both of these things very well, so they need to pick a strategy. They can invest in reproduction, which makes them a stronger colonizer, or they can invest in roots, which makes them a stronger competitor. More formally, natural selection will cause populations and ultimately species to exhibit a strategy that puts them somewhere on the spectrum of good colonizer, poor competitor, and good competitor, poor colonizer. This is obviously quite the simplification. Plant physiology and life history strategies are complicated. But keep in mind, our goal today is to get a broad idea of how these things might work, rather than some precise understanding of the evolutionary histories of grasses. But keep this in mind. We'll circle back to it towards the end of the video. So how does this trade-off affect our grass community and its fugitives? To help us think about it, I'll finally introduce to you the game of grass. Although by game, I really mean a famous mathematical model that I'm going to attempt to describe to you without using any math. Math minus math. Mathless math. I think it's a good thing. And as I'm describing this game, I want you to think really hard. I want you to ask yourself, are the grasses of the game good representations of reality? Or are they more artificial than the grasses that are in my hand? So if that's somewhat ominous start, let's get into it. What are the rules of the game? An imaginary field is broken into individual different habitats, or patches. Each patch is either occupied by one of 5 different species of grass, or is empty. Each species is given a rank on a competitive hierarchy. Rank 1, the highest rank, is the strongest competitor and the poorest colonizer. Rank 2 is the second strongest competitor and the second poorest colonizer, all the way down to the grass of rank 5, who is the poorest competitor and the strongest colonizer. Here are the rules of the game. Each turn, two things happen. One, every patch has a random probability of being disturbed. If a patch is disturbed, perhaps due to a flood, a plant pathogen, or a Labrador digging a hole, the occupant dies. 2, each individual grass on each patch disperses seeds to other patches. How many seeds an individual grass disperses depends on where it stands in the hierarchy, dispersing more seeds if it's a poorer competitor and fewer seeds if it's a stronger competitor. If a grass species disperses a seed to a patch occupied by a superior competitor, for example, if species 5 disperses a seed into a patch occupied by species 1, nothing happens.
Failure.
If a species disperses a seed to an empty patch or a patch occupied by an inferior competitor, it immediately grows into a full-fledged grass adult. In the case where a grass disperses a seed to a patch occupied by an inferior competitor, it immediately replaces the occupant. With this, we ask, what has to happen for all the grasses to coexist? First, let's think about how each species colonizes patches. Species 1 colonizes every patch its seeds disperse to. In essence, species 1 acts as if all the other grasses don't exist. A single individual in the field has the potential to colonize every other patch. Species 1 can survive in the field if it colonizes patches faster than it's disturbed from them. Assuming this is the case, species 1 will grow to occupy a stable proportion of the patches, leaving some open. Disturbances prevent species 1 from occupying every patch. Species 2 outcompetes all species except species 1. Patches unoccupied by species 1 are accessible to species 2. Species 2 needs to colonize the subset of patches unoccupied by species 1 faster than it is disturbed from patches for it to survive in the field. If this is fulfilled, species 2 will occupy some proportion of the remaining patches while leaving some open. Species 3 follows the same logic. It needs to make its living on the unoccupied patches left over by species 1 and 2. The same logic applies to species 4 and then to species 5. Overall, the lower a species is on the competitive hierarchy, the smaller the proportion of the environment it has access to because the superior competitors tend to hog all the space. Importantly, if you're a species low on the hierarchy, you face a double threat. If you colonize a patch, it's only a matter of time until you're given the boot by a superior competitor. In that interim time, you need to reproduce and colonize patches. Otherwise, you'll die out. The lower you are on the hierarchy, the fewer patches there are available to you because superior competitors occupy them, the less time you have until a superior competitor comes along because more species can replace you, and the faster your colonization needs to be to compensate. If it's fast enough, you can make your living by quickly escaping in the form of dispersing your offspring to unoccupied patches, a fugitive constantly on the run. While we only used 5 grasses in our game, you could theoretically get an infinite number of grasses to coexist if you assume your field is infinitely large. However, I have been informed by field ecologists that fields are in fact not infinitely large, so there's a limit to how this theory can be applied. And if you were to translate the rules of this game into math, what would you get? You'd actually get a few things. You can write down equations that define the abundance of each grass species, derive precise conditions under which poorer competitors will be able to coexist with superior competitors, and, important from a professional perspective, you would produce a particularly well-cited and influential paper. Of course, whether you buy any of this or not depends entirely on if you think what goes on in prairies is anything like the rules of our game. If you're skeptical, good. Overall, the competition-colonization trade-off constitutes an elegant hypothesis that makes intuitive sense to me. But how valid is it generally when describing nature? Well, like many things in ecology, it depends. As it turns out, evidence for the competition-colonization trade-off as a far-reaching explanation for the coexistence of species sharing common resources is mixed at best. In my opinion, there are 2 reasons for this. First, put bluntly, measurements just don't always find competition-colonization trade-offs. Maybe in many cases, this trade-off just isn't happening. For example, a recent paper reviewed previous studies that empirically test the competition-colonization trade-off. Of the 34 studies that fit the paper's criteria, 15, less than half, provide conclusive support for the competition-colonization trade-off. Why might this be? Well, it's certainly possible that some species are just better than others, at least at doing certain things, by nature of their evolutionary histories. Thus, it might be incorrect to think of all species as being on the same universal trade-off axis. Evolutionary history matters. Even if we were to assume all species share some kind of universal trade-off axis, it might be inappropriate to draw those lines simply on colonization and competition. This is because organisms have complicated life histories and have to deal with a number of different problems. For plants, this includes everything from dealing with drought to herbivorous insects to mutualistic ectomycorrhizal fungi. The list goes on in terms of the things that plants have to deal with. In short, species allocate the resources in a number of ways, not this abstract binary of competition and colonization. This simplification inevitably leads out a large portion of the broader evolutionary picture. Also, the terms competitive ability and colonization ability are hard to define. They encompass many things plants have to do, including reproduction, dispersal, and growth. That said, there are a handful of papers that find evidence of competition-colonization trade-offs. This includes plants like grasses, as well as other organisms such as birds, ants, marine invertebrates like mussels and barnacles, plankton, bacteria, ectomycorrhizal fungi, protozoans, rotifers, and even viruses. So perhaps we should rejoice and celebrate the competition-colonization trade-off in its diversity-maintaining glory. Sadly, this leads me to the second weakness of the competition-colonization trade-off, that it's a fragile coexistence mechanism. The competition-colonization trade-off model we just talked about assumes that there's a perfect trade-off between competitive and colonization ability. There are no outliers, and no species is both a good competitor and a good colonizer. Let's examine the implications of this assumption with our grass game. Let's look at a simulation of the game, the model, with 20 different species of grass. This plot shows the competitive rank of each grass species on the x-axis and the colonization ability on the y-axis. This plot shows simulations of the grass model. The x-axis shows time, and the y-axis shows the proportion of patches each species of grass occupies in the community. If you run a simulation like this scenario, a perfect trade-off in which being a better competitor necessarily means being a poorer colonizer, all the 20 grasses coexist. However, if you add a little noise like this so that the trade-off is no longer perfect, the number of coexisting grasses drops to 4 species. Thus, a very strict trade-off is required. Any deviation from it causes a major collapse in diversity. However, I'm not aware of any ecological community where such a strict competition-colonization trade-off has been measured. For example, a study that examined a community of protozoans and rotifers indeed found a competition-colonization trade-off. But the trade-off is noisy in a way similar to our simulation in which very few species coexisted. Therefore, even if species experience a competition-colonization trade-off, it may be insufficient to explain species coexistence. Overall, it does seem like there's compelling evidence that in some ecological communities, species experience a competition-colonization trade-off. I'm personally convinced that it is a real thing. However, this is insufficient to conclude that the competition-colonization trade-off plays the key role or even an important role in any of these communities. In fact, to my knowledge, there's no study that unambiguously shows an ecological community for which coexistence can be primarily or solely attributed to the competition-colonization trade-off. That said, some work does suggest it might play an important supporting role. With all this in mind, is the competition-colonization trade-off a useful concept? Ecologists certainly seem to care a great deal. Hundreds to thousands of papers cite the idea, and it's something that's kind of ingrained in the canon of community ecology. Whether this is because the competition-colonization trade-off is truly a good and important idea, or it's because ecologists have a little bit of difficulty letting go of good ideas that don't end up being important, well, it's a little too early to say. As I see it, while the competition-colonization trade-off is probably not the final frontier of understanding species coexistence, it does present a fruitful basis to refine our understanding of how competition occurs in nature. In addition, the competition-colonization trade-off has been influential in conservation biology. For example, humans tend to move things around a lot. This includes species like grass. By moving things around and artificially boosting colonization rates, humans may change the math on the competition-colonization trade-off. If fugitive species persist because their superior competitors have limitations in their colonization abilities, the human tendency to homogenize the environment may result in the extinction of the fugitives. Secondly, as I emphasized in our previous video, superior competitors do worse in more disturbed environments. Humans are bona fide disturbers of the environment. Therefore, things like deforestation, which artificially increase disturbance rates, might, somewhat counterintuitively, put the strongest competitors at the greatest risk of extinction. Of course, a lot of this is very speculative. So if you take one thing away from these videos, let it be this. The next time you go to the beach and overturn some boulders, or the next time you dig up some grass, know that you might be causing the disturbance that allows the fugitive to escape.